my master research is about looking for an answer. We will try to find an answer that phenothiazine itself is a weak fluorescent compound with a constant yield of less than 1% in cyclohexane. And nitro group is a commonly known fluorescence quencher. By combining these two ideas, we have 3-nitrophenothiazine. Interestingly, it's highly fluorescent, have a quantum yield of 100% in cyclohexane. So we're trying to find answers on the journey of this topic. I'll do an introduction about phenothiazine and motivation, about why we're going to do this in a more detailed motivation, and literature research experiment, conclusion, and acknowledgement. So, phenothiazine is first known to this word as methylene blue. It's actually in an oxidized form of phenothiazine derivative. In a reduced form, it's colored. The oxidized form is blue. It's first synthesized by a German chemist in 19th century. It's the first fully synthetic drug, which means it's not extracted from animal or plants. And nowadays, there are many phenothiazine drugs that is in use. For example, phenothiazine is an antipsychotic drug, and promethazine is an antihistamic drug that's targeted for allergy, motion sickness, and insomnia. Phenothiazine is a good electron donor. Because of this property, it can be used in dye-sensitized solar cell. By combining this good electron donor with a acceptor, forming a conjugate system, a donor-acceptor system. And in this way, when light illuminates on the phenothiazine, intramolecular charge transfer will happen. The electron will be excited from the HOMO of phenothiazine to the LUMO of the acceptor over here. And from the LUMO of the acceptor of the dye, will pass on, the electron will be passed on to the conduction band of titanium oxide and go to the outer circuit. On the other hand, this oxidized donor will be reduced back by the iodide triiodide redox couple. This perpendicular arrangement have two advantages. First, the dye to TiO2 electron move very easily from dye to TiO2, and back transfer from TiO2 to the far away phenothiazine is difficult. So most of the light can be converted into electricity. Another application is donor for TADF. There is a famous paper that was published in Chemical Material in 2017. It was titled Molecular Design Strategy for TADF Emitter. They provide a list, a table of donors for TADF and acceptors for TADF. The phenothiazine was on the list of the donor. So here are some examples. For example, this was a working out group, and here is a donor-acceptor system for TADF molecule. And here, this is not phenothiazine, it's phenoxine. It's a donor-acceptor-donor system. Donor-acceptor-donor system. In this research, apart from TADF, they do mechanical chromonic luminescence. And here is another donor-acceptor-donor system that uses phenothiazine. Also, it can be used as a friend of supramolecule. Because of its free motion, so before its self-assembly into metal cage, it have many vibrational and relaxational degree of freedom. So it's weak fluorescent. However, after self-assembly, after it incorporates with metal center, its frame is limited. So the restricted intramolecular motion reduce the non-radiative factors, so it's going to increase, and they can use this for some application. And here are motivation. Again, why 3-nitrophenothiazine is highly fluorescent. You can see that in 5 solvents, saccharide, toluene, dichromethane, ethanol, and acetonitrile. The parent phenothiazine has content yield less than 1%. However, in non-polar solvent, PTZ and also 3-nitrophenothiazine has a content yield of 100%. So why? Are there other organic compounds with common quenching groups that are highly fluorescent and hot? And are there other phenothiazine derivatives that are highly fluorescent? Okay, so we'll do a literature research. And we found in this work, they were trying to do a molecular probe. This molecular probe is to sense the environmental nitration stress. So when there is no nitration species in the environment, it's non-fluorescent. And if this compound is nitrated, it's highly fluorescent. Before designing this final compound, they make 3 compounds to compare their content yield. Here we can see that the whole molecule, except for fluoride over here, is in the same plane because there is no methoxy that creating a steric hindrance. So in compound 4, the transition is the non-bonding to pi stock forbidden transition. So it has a very low content yield. And for compound 5, there is a methoxy group here. So it cannot be on the same plane. It's a little orthogonal. So it must be a charge transfer. The bond P over here is a strong electron withdrawing group. And adding 2 additional electron withdrawing group further increase the content yield to 52%. They also do the sensitivity test that when there is no nitration species, the content yield is really low. And with more and more concentration, the fluorescence intensity increase. They also do a selectivity test. And it had a good response toward the species that they want to test. And low response to others. And the other work here, that they were mainly doing aggregation enhanced emission. And there are these 4 compounds. There is a nitro group here, and we can compare their content yield. For 1A and 1B, we can see that this is a toluene group, and here is mesithyl group. The toluene group here can rotate freely, but mesithyl group cannot. So the additional steric hindrance over here reduces rotational relaxation pathway. So the content yield increase from 6% to 22%. Compare 1B and 2, it just change electron withdrawing group. So the content yield doesn't change much. And compare 1B and 3, interaction of the oxygen over here with the vinylic hydrogen over here, causing this part, except the mesithyl part, this whole part to be on the same plane. So again, it's a non-bonding to pi star forbidden transition. So it's non-fluorescent. Okay, here was a paper published in 1980. It was mainly focused on 2 substituted, not 3 substituted, 2 substituted phenothiazine. And their content yield are quite low. All of them have content yield less than 1.2%. And because of early research on phenothiazine is mainly on pharmaceutical application, so they have compounds like this. The research has shown that adding this aliphatic group on nitrogen help increase its bioactivity. So here is another research. They were making dyes. These were mainly focused on the synthesis, steady state, and the dye step characterization, such as how to put the dye on the fiber and how is the attachment of dye onto the fiber. So they didn't do much about they didn't do any time result measurement, and there's no computational approach, and not to mention the discussion of photophysical properties. And they have quite high content yield, but they didn't provide any explanation. However, in this work, we will provide explanation. In order to make a fair comparison, we synthesize a series of compounds. Organic synthesis and enzyme characterization and crystallography was performed by my colleague Yao Lin. Phenothiazine is commercially available. After nitration process, you will have nitro group will substitute at C3 position. There are other side products at C1, but it can be separated. And PTZCHO can be get by a Dolph reaction with hexamine. This is hexamine. And followed by a Schmidt conversion with a sodium azide. We'll have PTZCN. PTZOME is a little complicated. We have to use a palladium catalyzed coupling reaction to connect bromobenzene with a P-aniside. And we get DPAOME. And after ring closure reaction, we'll have PTZOME. Here are their photophysical properties. In PTZOME, you can see the red, orange, and green line represent cyclohexane, toluene, and DCN respectively. Cyclohexane, toluene, and DCN. So for PTZOME, we can see the absorbance is mainly focused in peaks at 320 nanometer, which can be ascribed to pi-to-pi star transition, because it doesn't shift much with increasing solvent polarity. Okay, for PTZ, it peaks at 222, and we can see here their emission. There is a progressive vibronic emission over here. And when we introduce electron withdrawing group, it starts to shift a little bit. It shifts from 320 to 340, and with increasing solvent polarity, the emission also redshift a little bit. For PTZCHO, the absorbance peaks at 380, and its emission peaks at 460, 470, and 530. The strongest electron withdrawing group, nitro group, redshift the absorbance peak to about 400 and 420, 430, and its emission peaks shifted to 510, 580, and even 700 in dichloromethane. Here we can also see a trend of increasing content yield in cyclohexane. For PTZ, OME, and PTZ, the electron donating group and the parent PTZ, the content yield is quite low. And when we substitute the C3 hydrogen with electron withdrawing group, the content yield start to increase to 6%, 43%, and to 100%. And also, it is obvious that this absorption and emission is localized excitation, since it doesn't shift much with increasing solvent polarity. And here, the strongest electron withdrawing group, PTZO2, shows a very obvious charge transfer character. At higher solvent, emission redshift very much. And here are additional photophysical properties. You can see that for PTZO and PTZ, their content yield is quite low. So their non-radiative decay rate is quite large. And when we introduce electron withdrawing group, you can see an increase in radioactive decay rate. This trend which is followed by the increase in content yield. And there are something interesting over here, the ETOH. These are the quantum yield for PTZCHO are about 40, 40, 40, 35, but this is 6. Why? There are two lone pair on the formyl oxygen here, and they will form hydrogen bond with ethanol, the solvent. And the formation of hydrogen bond increase the degree of freedom, increase the non-radiative decay rate from 6 to the power 6 times 10 to the power of 7 to 8 times 10 to the power of 8. Therefore, its continuity is quite low. Also, there is an interesting thing over here. The emission peak of PTZNO2 in ethanol ordered. And we provide an explanation for this. The NO2 group, the double bond oxygen have 2 lone pair, and the single bond oxygen that carries a negative charge have 3 lone pair. And these 5 lone pair will form hydrogen bond with a solvent. And that increase the K non-radiative rate to highest among these. And because this will resonate, and resonance means that bond distance will change, and that that increases the degrees of freedom. So this emission peak golden a lot compared with others. In order to do a deep dive into its photophysical property, we do a computational approach. Here we can see the ground state and excited state optimized structure for these 5 compounds. At ground state is bent, and we define this bending angle as we calculate a mean plane from these 6 carbon on the left hand side, and another mean plane with a 6 carbon on the right hand side. And there's intersection of 2 planes is a bending angle. You can see it's bend. And at excited state, it's a little more planar. And there is a change from 33 degrees to 30 degrees, from 12 degrees to almost 0 degrees. What caused that change? First, this bending is caused by sulfur. Sulfur is quite large, it's electron rich, so its electron density is really high. And if we introduce electron donating group, it will increase the electron density over here, so it will bend more. And if we introduce the electron withdrawing group, it will decrease the electron density over here, so it will this sulfur will become smaller and the bending angle will decrease. Okay. For the frontier molecular orbital over here, low HUMO and low HUMO, and excited state optimized. You can see the transition is mostly pi. And here is the localized excitation, which means that the pi always, the HOMO and LUMO pi is all about at the same position. However, this we can see obvious charge transfer here. HOMO is right away from the electron withdrawing group, and LUMO is electron withdrawing group involved in LUMO. Another interesting thing that if we focus on sulfur, for PTZ and PTZOME, there is a non-bonding orbital over here on the sulfur, and this provides a clue to our long-awaited question. Here was our angle definition, and here is the angle trend. Why PTZ and PTZNO2 have such significant continuity difference? It is because that the transition between HOMO and LUMO of PTZ is a pi bonding to a pi anti-bonding mixed with non-bonding. So it's a partially forbidden transition. And we can see this from our experiment and also from the oscillation strength. Here the oscillation strength is quite low. However, the transition between HOMO to LUMO of PTZNO2 is pi bonding to pi anti-bonding, which is an allowed transition. The oscillation strength is really high, it's more than 0.18. And this explanation is supported by the frontier molecular orbital shape over here. You see this is a pi bonding, and this is a non-bonding. Pi anti-bonding mixes with pi anti-bonding mixes with pi. And here is a pure pi bonding to pi anti-bonding. apart from this, we also do the molecule. We don't do the extinction coefficient measurement only in toluene because this experiment will consume a lot of compound. And we can see that extinction coefficients have a positive mathematical relationship between with the oscillation strength. However, in this, if we see this is a calculated absorption peak, and this is a calculated oscillation strength, and this is the extinction coefficient at the calculated absorption peak. We cannot see a relationship between this column and this column. It is because that there exists an error, uncertainty between the real situation and the calculated situation. For example, the PTZN02, the calculated absorbance is at 361 nanometer. However, PTZN02 over here, the absorbance isn't at 361, it's at 432. So if, let's say, we add this wavelength all at 70 nanometer over here, and we will have this wavelength. And the extinction coefficient on this wavelength, this trend, this increasing trend, matches with the oscillation strength we calculate here. So it's very small, very large, very small, very large. We also do we also examine its electrochemical property. Marcus-Weller equation was originally used for photo-induced electron transfer. Our case is not photo-induced electron transfer. However, we found the result of applying this equation into our case quite convincing, so decided to incorporate this result into our report. And the Marcus-Weller equation looks like this. It takes the E oxidation over here minus 0,0 transition and minus E reduction over here, so we can get the energy difference of charge transfer. This energy difference over here. And Marcus-Weller equation only calculates the thermodynamically how favorable this charge transfer is thermodynamically. It doesn't calculate the barrier inside it, it's kinetically. So we enter these parameters into this equation and have the following result. Okay, here, the larger the Gibbs free energy means the charge transfer is unfavored. So PTZ-OM and PTZ should have most positive delta G. So here they have most positive delta G. And from PTZ and PTZ-HO, PTZ-02, they should have a decreasing chain of free energy because there is more and more charge transfer. So we can see a decreasing trend of Gibbs free energy over here. So this satisfies with our result. And here is the compound appearance. These compounds have very weak fluorescence at solid state with handheld UV light. And this is quite interesting. It's very black. So we decide to investigate why it is black. And it turns out in its single crystal, it have a very organized packing. This is called herringbone packing, it's like a fish bone over here. And this packing has a very good pi-pi interaction. The ideal pi-pi stacking distance is 3.0 to 3.5 angstrom. And the distance between planes is 3.335. So this is within a pi-pi stacking distance, so it's have a very strong pi-pi stacking. Therefore, it absorbs much amount of light at solid state, so it's black. And we also did do a thermal deposition. This was done by my colleague Meng-Chi Chen. And we can see the thin film absorbance. Thin film absorbance, the orange line over here, and it's purple in thin film. The thin material absorbent over here, and comparing with the solution totally, their shape is quite the same. However, the peak shift a little bit. So we have a maximum absorbance at about yellow region. So it's a pure purple. And PTs and NO2 have very poor fluorescent, or I can say non-fluorescent solid state. No matter we shine it with UV light or inbuilt xenon lamp or external laser, it doesn't. The signal we get is only scattering light. Okay, here is my conclusion. So we find an explanation for that why PTZ and PZ with electron donating group exhibit have a very low quantum yield. It is because their transition is partially forbidden, since their pi anti-bonding is mixed with the non-monoorbital unstable atoms. And on the other hand, when we introduce electron withdrawing group, it reduces the energy level of LUMO and thus diminish the mixing of non-bonding. So it is allowed pi to pi star transition. And PTZ also have 100% quantum yield in cyclohexane and have a significant solvent conformism from 500 to 700 nanometer. Okay. Following is the acknowledgement. I would like to thank Professor Chou for teaching me so many things, and thank Professor Chang to come here, and thanks Professor Alex, and thank you to all of my lab mates. Okay, the questions will be welcome.
Right. So, Alex, you come a long distance. So, you're going to Q&A first.
Well, I have to ask questions, right?
Yeah, you start to ask questions.
Yes. Well, a number of questions. First, I'm excited by the fact that NO2 derived compound not only exhibits 100% quantum yield, but very strong solvatochromy.
Yes.
Which means that the dipole moment becomes large.
Yes.
Interacting with the solvent. What do you know about solvent interactions with charge transfer organic dyes and the possibility to measure the dipole moment?
Okay, so from here we can see that there is a little shift over here. So it means that in non-polar solvent there is no somatochromism, but in higher polarity solvent the solvent is polar, so it will arrange itself to match to satisfy the dipole moment of the molecule. Okay, so and so this is the charge transfer is already happening at ground state. And here at emission, you can see that the red shift, because at excited state it's charge transfer, so it's one side is positive, one side is negative. Okay, and then the polar solvent will arrange itself again to decrease the energy of the molecule. So we can see that in non-polar solvent, it's fluorescent energy difference is high, and in polar solvent, the ground state will rise a little bit, and the excited state will be stabilized a little bit. So the emission over here will the energy gap is decreased. So the light.
I think what Alex asked you is, do you have any quantitative type of method? Okay, try to measure the dipole moment. Have you heard about the Lippers plot? You have to use the Lippers plot, okay, to plot and to calculate what is the dipole moment difference between ground and excited state.
We didn't do the Lippers plot.
Come on, this is the introductory level of the photophysics. You can check my paper, you know. I mean, one out of the, say, 6 papers, my previous paper, should all have the Lippers plot. You never read it, you know.
And I believe that the dipole moment should be great, really, because it's such a strong solvatochrony. Together with rather little solvent change in the absorbance, it shows that the ground state dipole moment is low, but the excited state dipole moment may be high.
Okay, I will try to do a little stop.
Other question refers to your time result data.
Time result data.
Some of them show very nice correspondence to single exponential function of decay. The others show some deviations.
Oh, yes, there is
What?
some.
Yes. What does this mean, single exponential decay? And if there are deviations, what could be the origin of this deviation and how you can account them?
Okay, single exponential decay means that its emission is one pathway, okay, single pathway. And there exists some deviation in PTZOA. And after examining the absorbance, and we conclude that there's two possibilities. One is there exists some impurity in the compound. And the other two possibilities is that actually phenothiazine is a good electron donor, right? I mentioned, and with electron donating group, it will enhance its electron donating ability. So it means that it gets oxidized easily. If it oxidizes, it will lose electron. Okay. So the other two, the second possibility is that in that solution there exists PTZONE and oxidized PTZONE. Now, if this is a equilibrium, it's hard to get rid of. But I'm thinking that if I can do the, for example, adding some reducing agent or oxidizing agent to see if there is a change in the spectrum, might have the clue for why there is bi exponential decay in PTZONE.
Methods in fluorescence. You mentioned correctly that you had for fluorescent measurements, you had to use the samples with absorbance and excitation wavelengths lower than 0.1, right?
Oh, yes.
Why this restriction? Would you explain that?
Oh, there is such restriction because that if the concentration is too high, and during the measurement of quantum ion, the emitted light will be absorbed by the compound itself again, so reabsorption. So it will cause the quantum ion measurement to deviate, cause some error. So the concentration must keep at 0.1 to 0.11.
Yes, correct. Thank you.
Right? That's it? Too easy, you know.
Well, I will continue.
Right, come on.
With some break.
Fine. Okay, so I think Professor Chang doesn't have any, question. Okay, but well, let's put it this way. Okay, I mean, just kinds of critical. Well, I'm asking kinds of critical mass. Okay, of the whole paper. Okay, for example, say if you claim, say sulfur atom. Okay, really involved in the transition. Okay. And then that non-bonding is really important, okay, for you, okay, especially for those of the electron donating group. Okay, that means either, I don't know, I mean, homo or lumo involved in the non-bonding, and that gives you kind of transition sort of the forbidden. Then they will ask you, okay, did you compare with POZ, okay, phenothiazine? What would it be look like? Okay, I mean the quantity will be dramatic increase or what? Well, I mean, if I'm a reviewer, okay, you really emphasize all the time, say, silo, I mean, really play a major role to quenching the emission. Okay, then I mean, the reviewer immediately kind of will prompt around his kind of idea, say, what about replace sulfur by oxygen?
I have seen that replacing sulfur by oxygen, the quantity will further decrease a little bit. Okay.
Well, how come they don't increase dramatically? I mean, there's no non-bonding involved in the transition moment anymore. Okay, and besides, for the oxygen, that the ring, the 6-member ring, even is kind of much more planar. Okay, they don't induce too much about twist, motion, quench the emission. So how come? How would you explain, this phenomenon just kind of increases slightly for oxygen, but indeed, actually oxygen, long period, so can never involve in this type of the transition because the non-bonding is kind of too stabilized.
I think there is another explanation, and because sulfur is on the next row of the oxygen and have more electron, so maybe its electron density is higher, so it can the excess electron will participate in the pi anti-bonding orbital. But however, the oxygen is smaller, so it cannot. And
Yeah, but no. You are talking about the discrepancy between these two atoms, but indeed, okay, they give you this almost the similar type of the weak emission.
Yeah, weak emission.
Yeah, so once, I mean, despite of this kinds of discrepancy, it doesn't change at all. So that means that there should be something else to explain this. Am I right? I mean, if you say, well, if they have a dramatic difference in terms of the, say, emission intensity, then I buy that. But now it's because, I mean, it's not the reality. So you got to give us some explanation about how come, okay, oxygen and the S, okay, have these different kinds of the electronic property already, but in fact, they give you almost the same outcome of the photophysics, indicating, say, it is a weak emission for both. All right? I mean, I don't know how to explain it, but you claim at the beginning, say, this is a very important factor. Well, if this is a very important factor, then you have to kind of defend yourself. How come this doesn't happen in other compound and analogs, almost the same as PTZ?
Okay, so I think if I have to explain this, I'll do this simulation replace with oxygen or even selenium.
No, they will be the same. But what I'm saying, I mean, could you check the previous literature? Okay, I mean, how did they explain this? Okay, I mean, there must be a lot of people that did the POZ. Okay, and check that.
Okay.
See, I mean, how they have an explanation of the weak emission yield. Okay, maybe they involve the non-bonding of the nitrogen already, which I don't know. I mean, you just have to dig it out.
Okay.
Otherwise, I mean, how do you kind of defend your original, say conceptual, type of the strategy? Say, oh, the S is because of non-bonding. But apparently it is not. I don't see any of this. Okay, the thing I buy it is NO2 has a 100% quantum yield in cyclosane, which is a selling point, okay, of this study, which I believe. But for the rest, I don't see any kinds of. This is very classical. Okay, people know this all the time. Okay, and people know say not only this, but also POZ have a weak emission. Okay, but it's kinds of not the kinds of mechanism you interpret in your way. Okay, for example, say I never understand. I mean, in terms of the table that you say, oh, this is forbidden because of the F strength is kind of small. Then I multiply by something, blah blah blah, and get to the. Do you know that? I don't know what's the purpose of the calculation of the. Show me that kind of slide.
Okay, so it's.
I never understand your point of the how to use the so-called magic calculation to end up the data what you want.
Okay, so originally we found here we're trying to explain one thing that
How come you multiply, you add 70 nanometer, which I know that, okay? But how do you transfer your F strength, which is oscillate strength, okay, to the number that you calculate?
No, I didn't convert it. I said the trend match. This is small.
Match your calculation.
The first, the oscillation strength should have a positive relationship between with the extinction coefficient, right? But here we didn't see that.
Now I know what you mean. Okay.
Okay.
You know what he does actually? Actually, he used this calculate one, and add the 70 nanometer and check the epsilon over there. Am I right?
Yes, because here.
But what's the point of that? I mean, this is your theoretical approach. Okay, and then add up the 70 nanometer to somewhere over here is your experimental result. I can never see anybody okay that can add up the experimental and the theoretical result together and to show you say this is supposed to be like this.
Yeah, of course.
How come you can do that?
Of course, this is an unofficial way, but we're trying to explain why here the extinction coefficient doesn't have at this wavelength doesn't have the trend with oscillation strength, because there exists different. You see, PCC and O2, calculate result.
Yeah, but let me ask you, okay, if you can find out any literature, okay, through the previous 100 years, okay, they can do like this, then I buy it. Okay, then I buy it. Okay, otherwise you create something which is for the Nobel Prize potential of the approach. I never seen this kind of approach actually. Okay, unless you told me say somebody used this, okay, as an evidence, okay, and with some explanation, then I believe. Otherwise, I don't see any reason. I mean, how come we can use that? And this is the same as I told you many times already. Okay, see, using Markov's theory, okay, and then you use all right. Go to the Markov theory. Right. See, this is the same thing, okay? I mean, all right. I mean, I sort of buy this. Okay, you can use the oxidation potential, reduction potential, okay, to simulate your NO and your the other sides as the hormone number. Okay, I sort of buy it. But here, okay, I mean, this radius, okay, of the chromophore, okay, that used in the Markov theory as the separate the chromophore for the weak electron transfer. That means that actually orbital has been separated fully. Okay, so you can use the radius of here and radius over here. But in your case, actually, all the chromophore is kind of mixed together. You even cannot find out where's the center. Okay, this is the center of the neutral chromophore. Where did you put your neutral center chromophore to I don't know to a chromophore that that define how to define this and this.
Professor, let's put it this way. Actually, from these parts, these are all minute adjustments.
I know that. Okay, I fully agree with you. I don't fully agree with you, but let me ask you one thing only. Okay, so the same thing. Okay, the same question. So the previous 100 years, is anybody using the intramolecular? The charge transfer like a TADF? A lot of like this, and use your equation, use this equation to calculate delta G. If you told me yes, then I buy it. Okay, so the previous, not previous 100 years, okay, say past the 3 years or 5 years, okay, and the same as kind of this intramolecular type of electron transfer, which is kind of mixed with the orbital like this, okay, including TADF, including a lot of the charge transfer compound, okay. Numerous, I cannot count it, okay, but anyway, countless. Everybody using this one, okay, and say these kinds of previous, okay, and then just usually say, oh, that's a trend. There's no charge transfer, that's a charge transfer. Anybody use these kinds of formula?
I haven't seen that.
Well, I haven't seen it either. So you created the Nobel Prize #2.
I'm trying to.
But no, you're not trying to. That's trying to. Are you sure? I mean, you can pass this paper to the reviewer, assuming the reviewer they are all idiots. They don't know anything about that. Okay, I mean, don't you think that sometimes your thinking, your thought is too naive, okay, to shoot for the science, because science has been kind of a groove, okay, this way that people start to realize everything, okay, fundamentally, and up to this point, okay, and then you try to create the point which is groundless, and then to convince the people, say, hey, this should be like this, okay. Well, if you talk to the student will buy it. But you talk to the reviewers, okay. If reviewer buy it, then this paper has been accepted. That means this journal, I'm going to stop submit to the journal anymore, because there's no grounding of the fundamental to use those kinds of the formula. See, this is the problem of it. The same as you calculate the extinct coefficient. I don't see any. Actually, I never see any place in any journal they use this type of the calculation and to end up say, oh, this is the trend. Okay, we ended up like this. I don't see it. Okay, that means that your calculation and your experimental result doesn't fit each other. For some reason, okay, that means that maybe B3 LYP doesn't fit to your calculation, because charge transfer, people told you already, all the physical property, okay, except for something I forgot, maybe wavelengths, okay, that B3 LYP can never fit charge transfer type of property. And you still use the B3 LYP. How come the reviewer can accept that? Could you use the other kinds of calculation? I think maybe B3 LYP is the only method you know that. Okay, you have to use the other type, like a CM or blah, 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 or even high level. Okay, try to fit your experimental result to repeat, but I can tell you from your, check the assumption, back to the assumption spectrum. See, the experimental result, okay, I mean, if you did right, they cannot be challenged. Okay, so if this is the extinct coefficient you measure correctly, the indicator saying your calculation should be wrong, unless there's something over here. If you expand it, okay, please, okay, don't measure up to say 0.1 of absorbance. We are looking at absorbance. We're not looking at the checking the content yield or checking excitation spectrum. So using the high concentration to see is anything over here, I don't believe, because your calculated say absorption maximum told me already this is all forbidden. If this is all forbidden, they tell you say it doesn't fit unless your measurement of the extinct coefficient has a lot of deviation. That means that this maybe have 100 times or 10 times difference. Otherwise, they're all almost the same.
By the way, why it is so low?
So low in what?
Yes, extinction coefficient.
Actually, this is low already.
Yeah.
So let me say this should be high to me. But for his, I mean, for his kinds of the measurement, they're all the same. Are you sure this is not well, this is not normalization, because I don't see any normalization point. But what I think Alex pointed out is 4 times 10 to the 3. It's low. It's very low. That means that this is forbidden already. So if I'm talking this is forbidden, maybe it is okay. But here and here, it's not okay because it's too low. Unless you can get here, this one is here, this one is here, then I believe.
So 5,000 is still too low.
Do you know what's the allowed tradition is extinct coefficient?
10,000.
Huh?
Maybe up to 10,000.
The fully allowed is about 5 times to 10 to the 5th. It depends on bandwidth. Okay, but normally for organic compound, and we did for the proton transfer or blah blah blah, it's always around 10 to the 4th, 10 to the 5th. Okay, and yours is a kind of say like this. it's a 4 times 10 to the 3. Okay, it's a 3-4 times less. Okay, and for this, if this is fully transition allowed. Okay, well, one thing can tell you already. Let me ask you. Okay, this one, you say in cyclohexane. Tell me, so what's the lifetime? Lifetime in cyclohexane.
Between 1 to 5 nanometer.
Well, this one, 7.62 nanosecond, right? Okay, so 7.62, that means it's about allowed. Okay, you can calculate this way. The trouble is, I mean, when in Tsinghua University, you didn't learn any spectroscopy, and in Taida, you don't learn anything either, okay? And I'm going to teach the spectroscopy, okay, I mean, the next term, okay? Well, probably can stay here, but anyway, okay? So if you didn't learn anything, okay, I remember it's where else is here? Yeah, see, this guy, I think did you take my course?
No.
But you did take my物化2嘛，对不对？ Who take my course before? No one. This guy, are you sure? You took my course? 物化2而已嘛 okay. So see, no one take my spectroscopy course, okay? I think this is the problem. The problem is, I mean, you don't have any fundamental grounding of that, okay? 7.62, I can tell you, okay, epsilon value multiplied by 10 to the 4th, okay? They almost give you inverse of this, almost give you lifetime, okay? Which is all, see, 10 to the 4, multiplied by 10 to the 4th, inverse of this, that means 10 nanoseconds. So that means this one has to be around, say, 2 times 10 to the 4th, about. Okay, let's check here. Okay, OME. So this is allowed too. See, 0.29. See, wait a second. You told us your PLQY is kind of low. For which one? They are not low. They are not low. They are 0.16 is okay, right? 16%. Am I right?
I'm sorry. The unit of PLQY should be
You got it wrong.
should have percent over here. So this is 100%.
Oh, it's percent over here.
Percent. I missed that. Sorry. It's a percent over here.
All right, percent. Okay, percent. All right, let's calculate it. The Ki is what? 7.5, 10 to the 6. And the Ki is, this Ki is, okay. See, here and here, okay, you can check it, okay, 10 to the 8, 10 to the 6. But this is 1.31. So about 20 times difference. Am I right? About 20 times.
Yes.
100, and this is about 20 times. That means that your extinction coefficient, if your bandwidth is about the same, that means that your extinction coefficient of this one has to be 20 times less than this one. Did you see that? I don't see anything. So even put this way, okay, if he's going to cheat everybody, okay, he can never kind of convince a good reviewer. But if I'm going to cheat a reviewer, I can do that easily, you know, because I just kind of reversely calculate, okay, and put over there without doing experiment, okay, I can pass my paper being accepted, okay. So see, a good knowledge people, okay, they always can do something which is, I mean, let the paper publish. This is the what I'm saying is the guy. What's this guy in previously in Bell Lab, Chang, okay, he published about 10 science papers, all fake, because he used his knowledge to calculate, okay, and then get the result, okay, and then send to the science, and get the publication, okay. So though it's a fake, okay, I can tell you, if I'm kind of powerful guy, I'll immediately hire him, okay, because this guy's knowledge is the best among all the researchers. Okay, it's so good, but anyway, ethically, okay, it's not allowed me to hire him. But what I'm saying, this guy's knowledge must be tremendous. Okay, otherwise he can never kind of say cheat those kinds of outstanding review and get it passed, you know, for the science paper. So this is the same thing. This still has to be 20 times difference. I don't see any. You've got the same thing. Okay, so something wrong with that. Okay, I mean either.
So what I would suggest, there is a simple method to calculate the radiative lifetime from absorption
Yes.
From absorption cross section.
Yes.
Right?
Yeah.
Let him do the opposite. Calculate absorption cross section from radiative lifetime.
Oh, yeah, yeah. So
Yes.
you mean doing some of the semi-cheating process? Yeah, that's what I'm saying. I mean, so see, I mean, it's too bad. I'm saying is, see, people come over here without any knowledge about the spectroscopy and dynamics. Actually, without any knowledge about sort of the exact state physical chemistry. Okay, and then 2 years, it's just too short for the time. Okay, for them to learn anything. See, this is the problem, you know, and sort of thing like this, you know. Well, following his, Alex' suggestion, okay, just kind of treat this as the correct data, okay, and go back to calculate what's the epsilon value. You know? That's the only way, you know what I mean.
Well, I'm thinking about the applications of this result. What can you say about that? You probably thought a lot of how to apply this new knowledge.
Okay, this application, I believe, if we understand these photophysical properties of these compound, and further, and others can use these knowledge to design a better molecular probe for the relativity detection.
Don't say molecular probe. Which one, what you are going to probe? Solvent polarity. There must be 5,000, you know, compound that can probe the solvent polarity. So what kinds of probe? See, if you say something that if you will find fault with that, okay, say, all right, probe what?
Well, may I ask you one question? Do you know anything about electrofluorochromism, or Stark effect, it is called in physics? Well, general approach is that if the dye is solvatochromic, it is also electrochromic, because solvatochromism, which means interaction with surrounding dipoles, gives you the shifts of spectra because of stronger interaction energy, right? But imagine that the dipoles, instead of dipoles forming the local efficient electric field, you have applied electric field. In this case, if the dye is oriented along the electric field vector in one or opposite direction, you will get this strong spectral shifts. I expect that. So in one direction will be blue shift, in opposite direction will be red shift. This is not so easy to establish in experiment, but there is one system with which we worked some years ago, which allows not only to establish this electrochromism, but also to get information about electrochromic properties. Surprisingly, the system is very simple. It is phospholipid membrane, because the gradient of electric field in membrane is 10 to 5 power volts per centimeter. So very great gradient, and the major component is so-called dipole potential. So
You mean the kind of gradient is what? Is created naturally?
By arrangement of phospholipids.
Yeah, well, what I'm saying is that created by cell, say naturally.
Naturally, absolutely
But
naturally.
in what kinds of conditions they can create these kinds of dramatic, gradient?
Well, every condition and such gradient exists in all natural membranes.
Yeah, but what I'm saying is that anybody experimentally observe that?
Many people, except myself, not except by mainly by our group.
So you do mention kinds of sudden change of the something?
Yes, and there are possibilities to modulate the dipole potential by dipolar compounds. So there is such a possibility.
Right. You can send us the relevant, publication. Probably I can take a look and see what's going on. Right, but if you request him, okay, that means he is going to stay here forever. Right?
But this is really good possibility to apply this property for something essential. What is attracting that the dipole moment is created by introduction of electron accepting group instead of electron donor groups, which are common for different fluorescent dyes, used for solvatochromism and electrochromism studies. Do you know many such examples?
No. I heard about it, but because there's no piece of very solid evidence. Okay, so normally I didn't pay too much attention to this. Okay, well let's put it this way. Okay, well the thing when the biophysics they produce something. Okay, I have to be put some question mark. You know why? Because the environment is so fluctuating. Okay, very difficult to repeat. But if this is a physics people, they report something, I have to pay attention in that. Okay, this is kind of different. I know that. Okay, I think you realize that there are a lot of the experimental results, especially for the biology type of approach, they can never be reproduced. The reason is because the system fluctuates. It's very difficult to follow up. But for the pure physics, okay, I mean when they say something, they indicate they do have something insight. Okay, you can dig it out. So I don't know. I mean, it really depends on what you are going to, But of course, in terms of significance of the result, the bio result will be much more significant because, I mean, it's related to our nature. Okay, but anything kinds of a human made. Okay, you just have to be careful. So I think this is kind of different type of approach. But anyway, okay, if you have a relevant type of publication, okay, I do appreciate you can send me the kinds of relevant publication.
Okay.
All right, so it just kind of follow up. I mean, I really don't know. I mean, we had to find out what's the significance behind. And I think both Alice and I agree. Say the one of interesting point, of course, is NO2 with high quantum yield. Okay, but yours is not kind of sole case. It's not a single case. Okay, I mean the people published some already. Okay, and the reason I believe how come the NO2 is kind of the with a good kind of quantum yield, I believe it's because of the nonpolar solvent. Okay, so in the case there's no, you're not talking about big solvent relaxation. Okay, so in the case, I would say just kinds of they are subject to the kinds of the inner environment. Okay, that's why, you know, okay. And besides NO2, the non-bonding is not involved. Okay, and maybe you claim, say, sulfur atom is not involved either, okay, in terms of the non-bonding. And that's why they got a good quantum yield. Otherwise, you know, it's difficult for me to find out, you know, what would be the kinds of the say remarkable point that we can point out, you know, from the study, you know, because and please just check the oxygen one, okay? Maybe the oxygen one they got the, you know, how come they got the similar result, okay? Okay, put it this way, okay, for the oxygen, if you claim this is kind of a small quantum yield too, what about say put the NO2 in the same position? Okay, what will happen?
So what do you suggest?
Well, I'm suggesting.
What position? Sorry.
No, I say, I mean, it's easy to purchase POZ, which is oxygen.
Yes.
Okay, to replace the sulfur, right? And put in the same position as the NO2, okay? Okay, and see what's going on. Yeah. What would be happening? Okay, if I don't know. I mean, they claim say from the forbidden to the allowed system. Okay, but it seems to me for the oxygen they all allowed. Okay, and then I don't see any reason unless put the oxygen blue shift further for the absorption. Then in that case maybe nitrogen non-bonding orbital is being involved. That would be different ball game. Okay, but I have no idea about this because see I'm not interested in this. This is a very classical, you know, about 50 years ago when I was a PhD student, maybe we'll do something like this. But you know, now it's a 50 years, half century later. You know, I'm not interested in this. All right, I think we are running out of the time. All right, that's it.